friend, welcome to this lecture, and in this lecture we will continue our discussion of finding n linearly independent solution of x dash equal to ax, and we have seen that we can find out n linearly independent solution provided that we can find out n linearly independent eigenvectors of the coefficient matrix A, and we have one result in this regard, that if we have n distinct eigenvalues of the coefficient matrix A, then we can find out n linearly independent eigenvectors, and with the help of these eigenpairs we can find out the n linearly independent solution of x dash equal to Ax, and we have seen one example. Now let us in that example we have considered that if we have say lambda 1, lambda 2, lambda 3 all are distinct eigenvalues, then we have find out the eigenvectors and we have written down the general solution of x dash equal to Ax. Now we move forward and let us assume that that if we have say complex eigenvalue, then how we can handle the situation. So here let us consider that let lambda equal to alpha plus I beta be a complex eigenvalue of A, right. So if we have a complex eigenvalue, it may happen, then the corresponding eigenvector, let us assume that it is given as V as V1 plus I V2 will also be a complex eigenvector, and in this case we will get a complex valued solution, that is xt equal to e to the power lambda t v of the differential equation x dash equal to Ax. But since all these problems are coming from real world problems, so we are interested in real valued solutions also. So from a complex valued solution we need to find out real valued solution. So our idea is to how we can find out two real valued solution from the above complex valued solution, that is xt equal to e to the power lambda t v, where lambda is alpha plus I beta and v is v1 plus I v2. So from a complex solution how we can find out two real valued solution, that is what we wanted to discuss here. So in this we have the following lemma, that let xt equal to yt plus izt be a complex valued solution of x dash equal to Ax, then both the real part and the complex part are real valued solution of 9. So it means that we have xt equal to e to the power lambda t v as a solution, and since it is a complex solution I can write down this as yt plus izt, where yt is real part of this xt and zt is the imaginary part of this. Then this lemma says that this yt and zt be two real valued solution of 9, and we can also prove that they are linearly independent solutions. So first let us prove that these are real valued solution, for which we simply say that since xt is a solution of this, so it will satisfy here. So let us write down xt equal to yt plus izt, and xt is a solution of x dash equal to Ax, so it means that y dash t plus I z dash t must be equal to A times yt plus I z t, and if we simplify the real image, we separate the real imaged part, we have y dash t equal to A of yt and z dash t equal to A of zt. So it means that yt and zt separately satisfy the system x dash equal to Ax, and hence we can say that the real part real of x of t and imaginary of x of t, that is here it is yt and here it is zt, will also be a solutions of x dash equal to Ax. Okay. So once we have this lemma, then we can say that if we have a complex solution, then from that complex solution we can obtain two real valued solution of x dash equal to Ax. So now let us consider the following example. So solve the initial value problem x dash equal to Ax, where A is given as 1 0 0, 0 1 minus 1, 0 1 1, and x0 is 1 1 1. So here let us focus on finding the particular example rather than finding the general solution. Of course, you can find out the particular solution after fixing the constant C1, C2, C3. So, let us see how we can find out a particular solution of the system x dash equal to Ax, where x0 is given as 1 1 1. So, first thing is we need to find out eigenvalues and eigenvectors. So, let us calculate the eigenvalues here. So, you find out characteristic equation. Characteristic equation is a minus lambda I equal to, determinant of this is equal to 0. So, 1 minus lambda 0 0 0 1 minus lambda minus 1 0 1 1 minus lambda equal to 0. So, determinant of this is equal to 0. So, 1 minus lambda times, you can write down minus 1 minus lambda whole square plus 1, and that is all, it is equal to 0, and you can simplify 1 minus lambda into 1 plus lambda square minus 2 lambda plus 1, and you can write down this as 1 minus lambda into lambda square minus 2 lambda plus 2 equal to 0. So, this is your characteristic equation, and here you can find out one root from this, and that is lambda 1 equal to 1, and you can find out the second root from this, that is lambda square minus 2 lambda plus 2 equal to 0, and when you solve this we can get a complex root, that is 1 plus minus I. So, let us denote this as lambda 2 as 1 plus I and lambda 3 as 1 minus I. So, because they comes in a conjugate pair basically. So, now let us find out the eigen vectors. Now, it is also obvious here that 1, 1 plus I and 1 minus I are all distinct eigen values. So, here one thing is very much sure, that we will get linearly independent eigen vectors. So, first let us find out the eigen vectors. So, for eigenvalue lambda 1 equal to 1, let us assume the corresponding eigenvector is given by V1, V2, V3, and we can find out V1, V2, V3 as solving this A minus lambda 1 I V equal to 0. So, lambda 1 equal to 1. So, we have 0 0 0 0 1 minus 1 0 1 0 into V1, V2, V3 equal to 0 0. So, if you simplify, this is equal to what? That minus V3 equal to 0 and V2 equal to 0. So, it means that here V1, V2, V3, then V2 and V3 must be 0. So, the only possibility left out is that V1 is arbitrary. So, V1 is arbitrary. So, let us take V1 as value 1. So, we can say that V is equal to 1 0 0 is an eigenvector corresponding to lambda 1 equal to 1, and the corresponding solution is given by x1 t equal to e to power lambda 1 t, that is e to power t into 1 0 0. So, here one real value solution is obtained by this. Now, second real valued solution we want to find out, but here we have a complex root, that is lambda equal to 1 plus I. Now, eigenvector, corresponding eigenvector, we are writing u1 plus I of u2, and the eigenvector we can find out like a minus lambda I into u equal to this thing equal to 0. So, a minus 1 plus I u equal to 0 is minus I 0 0 0 minus I minus 1 0 1 minus I u1 u2 u3 equal to 0 0 0. So, this is what minus I u1 equal to 0 and minus I u2 minus u3 equal to 0, u2 minus I u3 equal to 0. So, first equation gives you that u1 equal to 0, and second equation gives you that minus I u2 minus u3 equal to 0. So, you can say that u3 is equal to minus I u2, and third last equation is that u2 equal to minus I u3. So, you have u3 equal to minus I u2 and u2 equal to I u3. So, let us take u3 as a 1, and you can find out u2 as I here, and you can check whether it is satisfying here. So, u3 you are getting as minus I into I. So, that is 1 here. So, it means that it is satisfying. So, it means that your u is coming out to be u1 is 0, u2 is I and u3 is 1. So, 0 I 1 is your eigenvector, that is u. So, u is written as 0 I 1 as a eigenvector. So, you can find out the solution complex eigenvector complex solution as yt plus izt equal to e to the power 1 plus I t into 0 I n 1 here. So, now we can simplify this, we can simplify as writing here as this is nothing but cos of t plus I sin t, and here we have say 0 say 0 0 1 plus 0 say I, and this is 0, and from this we can find out the real and imaginary part, and we can write down here this as I times here it is 1 only. Then we can write down the solution real part, you can simply say that it is you can simplify it is cos of t into 0 0 1, right, and here you will get minus sin of t 0 1 0. This is the real part, and imaginary part will be cos of t 0 1 0, and imaginary part is also here it is sin t 0 0 1. So, it is your real part. So, your yt is given as you can write down sorry e to the power t is missing here. So, your yt is coming out to be e to the power t, and it is what, let me write it here 0 minus sin t and cos of t. So, real part is given as e to the power t into 0 minus sin t cos t, that is written here, and zt you can find out e to the power t times what is your solution 0 as cos of t, and in it is sin t. So, your imaginary solution is given by zt into e to the power t 0 cos t sin t, and you can easily verify that these are linearly independent solutions. For that you can simply take t equal to 0, and if you take t equal to 0, your y of 0 will be what, y of 0 is equal to 0 0 and 1, and z of 0 is coming out to be 0 1 and 0, and you can check that these are linearly independent vectors in R3. So, it means that yt and zt are also linearly independent solution of x dash equal to Ax. And if you look at here we have not solved for lambda equal to 1 minus I, because if you solve lambda for lambda equal to 1 minus I, you will also get the same real and imaginary part. So, here in the case of complex roots, we take one root, say among the pairs you take one, say one element, let us say lambda equal to 1 plus I, and with this we try to find out complex solution, and then we can find out two real solution given by yt and zt. So, now we have three linearly independent solution given to us. So, we can write down our general solution as C1 e to the power t into 1 0 0 plus C2 e to the power t into 0 minus sin t cos t plus C3 e to the power t 0 cos t sin t. So, this is your general solution, we can write it like this. But we want to find out a particular solution, it means that we want to find out a solution which satisfy the initial condition given at 0 as x of 0 as 1 1 1. So, now with the help of this we can fix our C1 and C2 and C3. So, we can fix that let us say that x of 0 is 1. So, it means that at t equal to 0 we have it is 1 1 1. So, if you look at this, here it is C1 and here we have 0. So, C1 is equal to 1, and if you look at the second thing, here we have 0. So, we will not get anything, here also we will get 0, here we will get C3 equal to 1, and if you look at the third entry, that it is 0 here, it is you will get C2, and here also you will get, so C2 is also 1. So, it means that here C1, C2, C3 all are 1, and you can find we can find out the particular solution by putting C1, C2, C3 as 1 1 1, and we can write down the solution as e to the power t is common in everywhere. So, you can write down e to the power t out. So, it is 1. So, 1 at first place, second place it is minus sin t plus cos t. So, cos t minus sin t, and in third place we have cos t plus sin t. So, we have this thing. So, this is the solution of x dash equal to a x with the initial condition that x of 0 is 1 1 1, and we can check that it is actually a solution of this. Now, moving on, so it means that we have discussed the case when we the roots are distinct. First case was distinct and real, and second case when distinct but complex, and we have we have seen one example in each case. Now, let us move in the case when we have equal roots, because in case of distinct root we have the guarantee that the corresponding eigenvectors are linearly independent eigenvectors, and we can find out the solutions. But in case of equal roots, that theorem will not be applicable, and we can say that we can consider the thing that if the characteristic polynomial of A does not have n distinct roots, then A may or may not have n linearly independent eigenvectors. So, that we can understand from this following example. So, in this example we consider 3 different matrices, say A, B and C. Each one is having same set of eigenvalues, of course repeated eigenvalues, but number of linearly independent eigenvectors are different in each case. So, let us say with this example we try to see that in case when we have repeated eigenvalues, then there is no guarantee at all that it has n linearly independent eigenvectors or not. So, let us consider the following example. So, first example, let us take A as identity matrix, say of size 3 cross 3. So, we have 1 0 0 0 1 0 0 0 1, and we can see that A has 3 repeated eigenvalues. We can check that eigenvalues of this, we have to write down A minus lambda I is equal to 0. So, this implies that lambda 1 equal to 1 equal to lambda 2 equal to lambda 3. So, here we have 3 repeated eigenvalues, that is each one is equal to 1, and hence the previous theorem that distinct eigenvalue will give you linearly independent eigenvectors will not be applicable here. But still in this case we can find out 3 linearly independent eigenvectors of A given as follows. How we can say, you take lambda 1 equal to 1 and look at here A minus say A minus I is equal to V equal to 0, and here we have 0 0 0 0 0 0 0 0 0 and V1 V2 V3. So, here we can have 3 linearly independent solution, and it is given as V1 as 1 0 0, V2 as 0 1 0 and V3 as 0 0 1. So, in this case though we have repeated eigenvalues, but still we have linearly independent eigenvectors, and we want 3 linearly independent eigenvectors and we are getting 3 linearly independent eigenvectors. Now, consider the second matrix. Here in diagonal entries it is all 1 1, only one entry is say non-zero, because in previous case only the diagonal entries are non-zero, rest are all 0, but here we have just perturbed our identity matrix and we simply took one non-zero value at this 1 2 place. So, B is just a perturbed case of A. So, here also we can check, since it is a say upper triangular matrix, we can easily check that the eigenvalues are nothing but diagonal entries. So, 1 1 1 is also a repeated eigenvalues in this case also. So, in this case also we have repeated eigenvalues and each one is equal to 1, but here we have only 2 linearly independent solution. How we can check? We can simply say B minus I, this is V equal to 0. Let us solve this, and here we have 0 1 0 0 0 0 0 0 0, and here we have V1 V2 V3 is equal to 0. So, here we simply say that your V2 has to be 0. So, it means that the condition is that V2 has to be 0. So, we have 2 free variable, that is V1 and V3, and we can simplify, we can find out 2 linearly independent solution as 1 0 0 and 0 0 1. So, here we have 3 repeated eigenvalues, but in this case rather than having 3 linearly independent eigenvectors, we have only 2 linearly independent eigenvectors. So, here we simply perturbed our identity matrix by at only one position, but the result is very disappointing, that here we are not able to get 3 linearly independent eigenvectors. Now, consider one more case. Here we again perturbed our matrix B, and in place of having in only one place we have changed in B, but now here we change the value at 2 different places, that is in diagonal as well as the above diagonal entries are also non-zero. So, here again, since it is upper triangular matrix, eigenvalues are nothing but the diagonal entries, that is 1 1 1. So, here again 3 repeated eigenvalues are given as 1 1 1, but here if you want to find out say eigenvector corresponding to lambda 1 equal to 1, then we have 0 1 0 0 0 1 0 0 0, and here we want to find out ABC as 0 0 0. So, here we condition is that B equal to 0 and C equal to 0. So, here B equal to 0 and C equal to 0 is fixed, so only one eigenvector is possible, that is 1 0 0. So, we have seen that 3 cases basically. In one case, in both the cases are having same set of repeated eigenvalues, that is 1 1 1. All the 3 are 3 cross 3 matrices, but in one case we have 3 linearly independent eigenvectors, in another case we have 2 linearly independent eigenvectors, and in the last case we have only 1 linearly independent eigenvectors. So, here we cannot, how we check that we are dealing with which kind of a matrix, that is A, B or C. So, in this case when we have repeated eigenvalues, it is quite difficult to find out n linearly independent eigenvectors. Of course, we are not denying that in some cases we may have n linearly independent eigenvectors, but it is quite difficult to check whether our matrix, given matrix, falling in that particular category. So, if we consider the following 3 linear system of equation, that is x dash equal to Ax, x dash equal to Bx and x dash equal to Cx, where A, B and C are the matrix defined in the example 4. Then in this case we have only 3 in the first case, 2 in second case, and 1 linearly independent solution of the form e to power t v, where v is 3 cross 1 is a constant vector. So, in first case we have 3 linearly independent solutions, second case we have 2 linearly independent solution, and third case we have 1 linearly independent solution. So, it means that only in first case we can write down the general solution, but in second and third case we may not write down the general solution in this particular situation. So, we need to find out the remaining linearly independent solution of this system x dash equal to Bx and x dash equal to Cx. Why? Because we have already have the guarantee that the solution space of x dash equal to Bx and x dash equal to Cx has a dimension n. So, they exist n linearly independent solutions. The only thing is that in this current situation we may not be able to find out in this particular form, that is e to power t into v. So, now in case of equal roots we need to have some other method to find out the general method, general solution. Suppose that n cross n matrix A has only k which is less than or equal to less than n linearly independent eigenvectors. So, it means that we have system x dash equal to Ax, but we are able to find out only k linearly independent eigenvectors, we are not able to find out the n linearly independent eigenvectors. So, it means that some of them must be repeated eigenvalues. So, in this case we have only k linearly independent solution given in the form of e to power lambda t and v. So, now for a given constant vector v. Now, we need to find out remaining n minus k linearly independent solution of this system x dash equal to Ax. So, here we get the idea from the scalar case, as we have pointed out that we have x dash equal to Ax, then the solution is given as xt equal to e to power at into constant. So, in first case what we try to do here, we take that this c in place of constant value, if we replace this c by a vector, it means that xt equal to e to power AT into that V, then under what condition this will serve as a solution, and we have shown that this will act as a solution provided that this A comma V is an eigenpair of A. So, corresponding to system x dash equal to Ax, this xt equal to e to power ATV is, will work as a solution provided that this AV is an eigenpair of matrix A, and we have seen that this will this works very fine provided that A has n distinct eigen values. Now, and in case of repeated eigenvalues, we may not have n linearly independent solution. Then our idea is now look at this this component. So, here we have two components is C and this. Here in the first case we have generalized this C as a eigenvector, C as a vector, and we try to work with this kind of a function as a solution. Now, in place of this, now let us generalize this. In place of this, let us try to see what happened. Can we define this kind of a solution where xt is equal to e to power at v, where v is n cross 1 and e to power at is some something similar to e to power at in a scalar case. Now, here how we define this matrix and whether it is defined or not. So, we may try first of all that xt equal to e to power at v as a solution, and let the matrix A B is n cross n matrix, and then the function e to power at may be defined as the limit of the following series, because here we are taking the motivation from the scalar case, and we know that in scalar case our solution e to power at is nothing but 1 plus at plus a square t square upon factorial 2 and so on. So, in case of when this a small a is replaced by a matrix, then can we have e to power at as I plus at plus a square t square upon factorial 2 and so on. Can we have similar kind of a structure, and if it is if we have this solution, if we have this kind of a structure, will it work as a solution of the system x dash equal to Ax. So, here we may define this as a limit of this infinite series provided that this infinite series converge. So, here first thing we need to work whether this infinite series will converge or not. So, to show that this infinite series converge or not, we use the criteria, that is Cauchy method of criteria. So, for that let us consider this Sn as summation I equal to 1 to say n this a I t I upon factorial I, this as a sequence of matrices. So, here this Sn is a sequence of matrices, and if you recall we have discussed the under what condition this Sn will converge to a limit. So, here we say that this will converge to a limit which we call this as e to power at. So, first thing we want to show whether this will converge or not. For that if you look at that we have one result in case of scalar thing, that xn is a sequence where xn is a sequence of partial sum, it will converge provided that it satisfies the Cauchy criteria, that for every epsilon greater than 0 they exist n naught such that modulus of xn minus xm is less than epsilon for every n comma m greater than n naught. If we have this kind of criteria, then the xn will converge and converge to some limit, let us call this as x. So, we are using this similar kind of result for Sn here. So, Sn minus Sm less than epsilon for every epsilon greater than 0, we need to find out n naught such that this is true for every n m greater than equal to n naught. So, only thing is that here this modulus is replaced by norm here. Is that okay? So, here we want to check that whether this Sn minus Sm Sn, this sequence Sn of matrices forms a Cauchy satisfy a Cauchy criteria or not. So, where Sn is defined as summation let us I equal to 1 to n a to power I t to power I upon factorial I. This will satisfy the Cauchy criteria or not. So, if you look at the Sn minus Sm, let us assume that m is bigger than n. We can, since m is not equal to n, so let us assume one way. So, norm of this is equal to norm of summation, here it is I equal to n plus 1 to m a to the power I t to the power I upon factorial I, right. Now, we want to show that this is less than or equal to 1. So, here we can use any of the norm, and we can simply say that here we are using this norm, that norm of a plus b is less than or equal to norm of a plus norm of b. So, we are using this summation. So, we can write down this as summation I equal to n plus 1 to m and norm of a I t I factorial I. So, now this norm of a I is some number, because norm is a function from space to a real line. So, all these are, so it basically reduces to your sequence of real numbers, and we simply say that if this is less than, if this can be made arbitrarily small, then we are done, then Sn is a Cauchy satisfies the Cauchy criteria and we are done. But if you look at this modulus of norm of ai, this can be further less than this. So, we can write it here, say norm of Sn minus Sm is less than or equal to summation I equal to n plus 1 to m. Here we have norm of ai t I and factorial I. So, here let me take this modulus of T n, and this can be further I can write it I equal to n plus 1 to infinity norm of a I and modulus of T I upon factorial I. Now, if you look at this norm of a is a particular number, then this is nothing but the tail of e to the power norm of a, right. So, this is the tail of this series e to the power norm of a modulus t. We already know that for fixed t this is a convergent series e to the power, this is further less than or equal to power okay. So, this is tail of, let me write it here, okay. So, here if it is a tail of this convergent series, then as n tending to infinity, this is tending to 0. So, it means that as n is very large, this can be made arbitrarily small, right. So, here we are using this fact that Sn is a sequence of matrices which satisfy the Cauchy criteria, and hence we can say that Sn will converge to some limit, and we call this limit as e to the power at. And not only this, we want to show that here if you look at your Sn is basically what? Sn is summation I equal to 1 to n a to the power I t to the power I upon factorial I, and we can say that this is norm of this is less than or equal to the norm here, which is we can write it here summation I equal to 1 to n norm of a I modulus of t I upon factorial I, right. So, norm of Sn is less than or equal to this. So, we can say that this we will require later. So, first thing we have proved that Sn is a sequence which satisfy the Cauchy criteria, and hence this infinite series will converge, right. And if this infinite series converge, we can define this value as e to the power at. So, we define this as e to the power at. So, it means at least this term that e to the power at makes sense. Now, we can also show that this infinite series converges uniformly for all t. So, for that we can apply the Weierstrass-Hammond test, and if you look at in this series, what is your nth term? Nth term is a n t n upon factorial n, and we can simply say that norm of a n t to the power n upon factorial n is less than or equal to norm of a power n modulus of t to power n upon factor n, and call this as Mn. We already know that this summation Mn is a convergence series. In fact, it is a part of, it is nothing but e to power, this can be written as e to power norm of a modulus t minus 1. So, it means we can see that this is a convergence series, and hence hence we can say that this term, let us so it means that this summation a n t n upon factorial n is also a convergence series. Not only convergence series, it is a uniformly convergent series. So, we can say that using Weierstrass-Mn test, we can say that the convergence of this infinite series to e to power a t is uniform, and we can also prove the following identity, that norm of e to power a t is less than or equal to e to power norm of a t. Here I have taken this particular example. Norm of a is you can take the supremum of aij is basically modulus of aij. We have taken this. You can take any kind of, and we can prove that norm of e to power a t is less than or equal to e to power norm of a into t. So, we have shown that this infinite series is convergent and converges uniformly to e to power a t. So, the limit we are defining as e to power a t. Now, since the convergence of this series is uniform, and hence we can differentiate this series term by term, and we can evaluate d by dt of e to power a t, and it is nothing but a plus a square t plus so on, and if we take out this a common, then it is a into I plus a t and so on, and this is nothing but e to power a t. So, we can write down d by dt of e to power a t is equal to a e to power a t. So, so here a t, a is n cross n, and e to power a t is also n cross n matrices. So, let us relate this with our system of linear equation x dash equal to a x, and we say that e to power a t into v, where v is n cross 1, then this will be a n cross 1 function. Then we want to show that we claim that e to power a t v is a solution of x dash equal to a x for every constant vector v. So, d by dt of e to power a t v is equal to a e to power a t, v is just a constant, so we can take it out, and it is nothing but a into e to power a t v. So, it means that x t equal to e to power a t into v is a solution of x dash equal to a of x, right. So, it means that if we can calculate e to power a t for a given matrix A, then we can write down this solution as e to power a t into v. But this problem of calculating e to power a t is a very difficult problem, because first of all e to power a t is an infinite series, as we have pointed out here. It is a very it is an infinite series, and calculating these infinite sum is quite difficult. So, here we have to find out certain tools by which we can simplify our procedure to sum this infinite series in a finite term. So, here we want to make note that if somehow we are able to find out e to power a t, then our solution are given to with the help of e to power a t v. So, now we want to find out n linearly independent vectors v for which this infinite series e to power a t v can be turned down to a finite series. So, everything will depend on this vector v. It means that we have to find out vector v in a way such that this e to power a t v is reduced to finite series. So, we need to find out this vector v, since for every vector v it is a solution. So, in particular if we put some condition on v, then also this e to power a t v will be a solution of this, and we want to choose vector v in a way such that e to power a t v is a finite series, or it can be reduced in just few terms, say 1 term, 2 term and so on. So, here we look at e to power a t v as e to the power a minus lambda I t into e to the power lambda I t. So, here one thing we note down here, that here it may not be true that e to the power a plus b may not be true for e to the power a into e to the power b. This is very say common in terms of scalar series, but in case of matrix series it may not be true, but it is true in a particular case when a b is equal to b a, right. So, in case of a b equal to b a, this e to the power a plus b can be written as e to the power a into e to the power b. So, this you can try, but in this case when a b equal to b a, you can easily prove that e to the power a plus b equal to e to the power a into e to the power b. I can take I can give you one hint, that let me e to the power t a plus t b minus e to the power t a into e to the power t b. You take this as a function, say f t, and show that this f dash t equal to a plus b f t. Try to show that this f t is a solution of f dash t equal to a plus b into f t. Here please observe here that e to the power t a, if we find out the derivative of this, it is a e into e to the power t a. Please observe here that you cannot write this as e to the power t a into a, right. It is not true at all, it may not be true. So, here f dash t equal to a plus b into f of t, and you can check that f of 0 is simply 0. So, if you can show that that f t is a solution of this with the initial condition f of 0 equal to 0, then f t has to be ideally equal to 0, and hence the result, it is true for all t. So, in particular true for t equal to 1 also, and we are done. So, here so far I have not used this condition, but while proving that f t is a solution of this initial value problem, you have to use this a b equal to b a. In fact, we have to we can show that if a and b commute, then a into e to the power b t will also commute. So, here assuming that you try at least once. Okay. So, using this condition that if a b equal to b a, then e to the power a plus b equal to e to the power a into e to the power b, I can write this e to the power a t v as e to the power a minus lambda I t into e to the power lambda I t. Here lambda a minus lambda I into lambda I is equal to lambda I into a minus lambda I. So, here we are using this condition. Now, I can, so e to the power a t v can be written as e to the power a minus lambda I t into e to the power lambda I t v, and e to the power lambda I t v can be written as we can write down the expression for e to the power lambda I t as I plus lambda I t plus so on, and if you take out this I square is same as I and so on, we can take out this I and we can write down this as this is e to the power lambda t, I into v is nothing but v. So, we can write down this as e to the power lambda I t v is nothing but e to the power lambda t v. So, it means that you can write down e to the power a t v equal to e to the power lambda t into e to the power a minus lambda I t v. So, here we have this simplification, that if we are trying to choose v in a way such that this can be truncated in a finite number of terms. So, this will continue in next lecture, and here I will stop. I will discuss this how to choose v in a next class. Thank you very much.